My name is Nurul Atika and my metric number is 216654, and today I'm going to introduce to you all the second law of thermodynamics and the thermal energy reservoir. Okay, so first look at this animation. We see that the ice cream melts. This shows that heat flow from higher temperature to the lower temperature. Okay, so the second law of thermodynamics state that the process is spontaneous and it can only reverse if there is an external work. So how about we reverse the melting process? It surely cannot be a spontaneous process unless we put an external work. So the second law of thermodynamics is related to entropy, which is the randomness in a system, which implies that energy become more spread out and less available for useful work if it increases. Okay, so now we see that for low entropy, the randomness is organized. Meanwhile, for high entropy, the randomness system is disorganized. Okay, so and the quality of the energy also will degrade over time. Okay, this law complies our topic when a refrigerator moves heat from a cold space to a warm space, which opposes the natural direction of heat flow, and it needs external work, but we'll go into details later. Next, we'll move to the thermal energy reservoirs. Okay, as you can see, this ocean is one of the examples for thermal energy reservoir. This is because ocean has a large thermal energy storage capabilities. So what exactly is thermal energy reservoir? Okay, so thermal energy reservoir refer to a body that can absorb finite amount of heat without any change in temperature. There are two types of thermal energy reservoir, which are heat source and heat sink. Heat source is a reservoir that supplies heat to a system. Meanwhile, heat sink is a reservoir that absorbs heat from the system. Okay, so the refrigerator is also related to the thermal energy reservoir. It is when the heat is extracted from low temperature reservoir to higher temperature reservoir using external work.
What is Carnot refrigerator? Carnot refrigerator is a refrigerator that operates on a reverse Carnot cycle.
As you can see in figure 6.5, no refrigerator can have a higher COP than a reversible refrigerator operating between the same temperature limits. So, this is the formula for any refrigerator or heat pump, and this is the formula for Carnot refrigerator or heat pump. The COP of a reversible refrigerator or heat pump is the maximum theoretical value for the specified temperature limits. Actual refrigerators or heat pumps may approach these values as their designs are improved, but they can never reach them. The COP of both the refrigerators and the heat pumps decrease as TL decreases. That is, it requires more work to absorb heat from lower temperature media.
All of us gather around because we are diving into a marvel of modern engineering that's all about comfort and efficiency. Introducing heat pump. Imagine a machine that does not just heat your home in winter, but can also cool it in summer, all while saving energy and being environment friendly. What is a heat pump? A heat pump is a device that transfers heat from a colder area to a warmer area using mechanical work against the natural flow of heat. The example of application: home heating, refrigeration, and air conditioning. It operates on the principle of the second law of thermodynamics. How does a heat pump work? First, by absorption, heat is absorbed from the source like ground and air by low temperature refrigerant in the evaporator. Compression, the refrigerant is compressed, raising its temperature. Condensation, heat is released into the target space indoors as the refrigerant condenses in the condenser. Expansion, the refrigerant is expanded to lower pressure, cooling it further.
Second law of thermodynamics and heat pumps. What is second law? The second law is heat naturally flows from hot to cold areas, but heat pumps require external work to reverse this flow. These are the formula for coefficients of performance, COP. Energy conservation combines work input and heat transfer to deliver more energy than consumed. Next, let's visualizing heat transfer. This diagram demonstrating the flow of heat and work through the system. this magnified view of the refrigerant cycle showing states like gas, liquid, and temperature or pressure changes at each stage. Where are heat pumps used? We use in home heating or cooling systems. We also use in refrigerators and freezers, and in industrial heating and cooling processes.
In this question, it is all about the Carnot heat pump. We have to determine the minimum power required to drive the heat pump. As we know, we have to maintain the 21 degrees Celsius in the house, and the outside temperature is negative 5 degrees Celsius, and the heat loss rate is 37.5 kilowatt. First of all, we have to find the coefficient of performance of the heat pump by using this formula, and then we substitute the value given in the formula, and then we got the coefficient of performance is 11.3. And then we now can find the required power input with the formula given, which is QH over COPH. We substitute the value, which is 37.5 kilowatt over 11.3, and then the answer is 3.32 kilowatt. And this is the power required to maintain the temperature of 21 degrees Celsius by the heat pump. Okay, so now let's move to question about refrigerator. In this question, it asks us to determine the electric power consumed by the refrigerator and the rate of heat transfer to the kitchen air. So now the COP is given and Q dot L is given, which is 1.2 and 60 kilojoule per minute. So first, to calculate the electric power, we just use this expression W dot net in equal to Q dot L over COP. So we just substitute the equation, and we got the answer 50 kilojoule per minute, and we can convert it to kilowatt, which is 0.833 kilowatt. For question B, it asks the rate of heat transfer. So we just use this formula Q dot H equal to Q dot L plus W dot net in, which is 60 kilojoule per minute plus with 50 kilojoule per minute that we already calculate in question A, and then we got 110 kilojoule per minute. So that's all for this chapter. Thank you.